To begin investigating the form then that these wave functions take at our specific allowed energies, we're going to proceed through the different regions, region 1, region 2, and region 3, and see what these conditions actually determine for us there. So if I look, for example, in region 1, I'm looking then at phi sub 1, right? And this applies for x values less than minus a. When I look at the solution there, I'm going to take the liberty of ignoring that constant prefactor, so I will just have this growing exponential piece. I can copy that down. And it just is a growing exponential. There's nothing really particularly interesting about this. There's no specific magic where the values of k over alpha come in. There's just a value of alpha and a certain amount of exponential growth. So granted, the first piece of the solution doesn't really have a lot of freedom in it. There isn't really a lot interesting going on there. But we write it down for the record. Let's now take a look at the second piece. Now the second piece is where things are going to become more interesting. Firstly, it has a much richer structure because we now have two terms, a sine term and a cosine term, and we also have alpha over k, which is taking on very specific values that determine for us these type 1 and type 2 solutions. So I would like to really understand much better how these specific values of k over a, right, factor into the behavior of the function that we see here. Now, k over a is either a cotangent or a tangent function, which then has sines of ka and cosines of ka. And what I also notice is that my solution itself can be written in terms of sines of ka and cosines of ka. I see I forgot my factor of k here, excuse me. That's a little annoying, right? Because if I were to expand out these trig functions, I would get cosine kx times cosine ka and minus sine kx times sine of ka. And likewise, there's a trig identity for the sine function, which will bring out all kinds of sines and cosines of ka, which may combine in interesting ways with the sines and cosines of ka inherent in this alpha over k. So what I'd like to do then is to expand out my trig identities for this function, and then to pick off what the specific values of alpha over k would be telling me. So first term is cosine of kx plus a. And the second term, has a sine function. And when I expand these, you'll notice I get two types of terms. I'll get cosine kx terms coming from the first one, and also some cosine kx terms coming from the second, and likewise for sine of kx and cosine of kx. So I'd like to deal with these one at a time and gather the common terms together. So let's focus on all the pieces that will be multiplying cosine of kx. Now, in doing this, let's see here. So cosine of kx plus a, when I expand that out, gives me cosine of kx times cosine of ka. And there's also going to be a sine of kx. I guess I may as well just collect these while I'm at it. There'll be also a minus sine of ka times sine of kx. So I've taken care of the first term. The second term has alpha over k times the sine of the sum of my angles. So that will give me alpha over k. Now, when I expand the sine, you get cosine times sine plus sine times cosine. So here's cosine kx. That means I need a sine of ka to multiply the cosine of kx for that part of the angle addition formula. And for this second piece of it, again, my prefactor is alpha over k. But if I have sine kx, when I expand out the sine of kx plus a, that means I will get a cosine of ka, multiplying it to complete the expansion of the sine function. So all I've done is really just gathered my prefactors together and rewritten out expanding out the trig identity. Now what I'd like to do is to see if there's anything special that happens to these factors in lieu of the particular values of k that apply for my bound states. And when I look at these terms, I notice there's something very familiar going on here. Notice this type 2 term in a type 2 solution, this term is 0. cosine plus alpha over k sine. But that is exactly what I have here, cosine plus alpha over k sine. So this term completely disappears for a type 2 solution. The type 2 solution has none of this. It has 0 here. It has no cosine piece. It only has a sine piece. That's interesting. Which also kind of makes me wonder, well, what about the sine kx term? Maybe something special happens to that one because there seems to be this interplay between 1 and 2 in the case of a type 1 solution. Now, if I look at a type 1 solution, if I multiply this through by alpha over k, I would get minus sine Ka, here it is, plus alpha over k cosine. So in fact, indeed, for a type 1 solution, it's this lower piece that disappears, and the type 1 solution only has a cosine of kx. So somehow, magically, these type 1 and type 2s that we factored into are designed, it seems, right? Something mysterious is going on here. They seem specifically designed to give me only sine or cosine type solutions in the two different cases. So let's then consider the cases specifically then one at a time. So if we focus on the case 1 type solution, so for case 1, we just learned it is the sine term that disappears. So I only have this cosine piece. And let's write down what that cosine piece actually becomes. So it's cosine Ka plus now alpha over k, remember, has a very specific value for a type 1 solution. That would be the reciprocal of the cotangent, in other words, the tangent, which is sine over cosine. So what I get is sine over cosine times sine gives me sine squared Ka over cosine of Ka. And all of that then is multiplying cosine of Kx. Now this is interesting. This looks like maybe I can do something with it also, right? I would love to get this on a common denominator. So let me write this as something over, I guess I got a little cramped here, but something over cosine Ka. And if I put things on that common denominator, the first term will become cosine, oh, look at this, it's beautiful, cosine squared Ka, right? And the next term becomes sine squared Ka. And we know cosine squared plus sine squared, of course, is the famous trig identity, which gives us 1. So this entire prefactor becomes 1 over cosine Ka, and I have this beautiful result that this term for case 1 type solution, phi 2, boils down to this very simple thing, cosine Kx over cosine Ka. What could be more simple or more beautiful? Now, it's really mysterious at this point why it became just a cosine. We could have guessed, though, once we knew it was cosine Ka, there would have to be a cosine Kx, excuse me. There would have to be a cosine Ka factor in the denominator. The reason is that if we were to evaluate phi 2 at x equals minus a, it has to match up with phi 1. And phi 1 at x equals minus a gives me e to the 0, gives me 1. So this has to be designed specifically to give the value 1 when x has the value minus a, and the way to do that is to include the cosine Ka in the denominator. So it's a very pretty result, but really the most mysterious part is why just pure cosine for this type 1 solution. Let's now look at type 2. So type 2, as we had said, is going to boil down to only a sine Kx type solution. So let's look at the prefactors on the sine Kx solution. Right, you will recall the cosine piece was exactly the type 2 condition, which gives 0. So we've got the sine solution is minus sine of Ka. Very good, minus sine of Ka, plus then alpha over K, times cosine Ka. Now, alpha over k for type 2, right, would be the reciprocal of this, which would be minus cotan of Ka. So it comes in with a minus sign, so there'll be a minus, and cotangent is cosine Ka over sine Ka. And so that's substituting in for the alpha over k, but notice the alpha over k has its own factor of cosine. So it looks very parallel to what we had last time. So that would become a cosine squared then, when I include this extra factor of cosine. Now looking at this, the first thing that strikes us, of course, is there's an overall minus sign that I could pull out. The next thing is that it has almost the same structure as what I had seen before. If I look at this trig function, it would have a sine Ka in the denominator, which notice lines up beautifully with the sine Kx, just like it had previously. So that seems to be designed just to match my wave function value to give me 1 at the end of the day. But let's carry it through and make sure. So putting this sine on the sine Ka denominator, yep, gives me sine squared Ka. The other term was clearly just this cosine squared Ka term. Once again, that's the famous trig identity. This just gives me a value of 1. So at the end of the day, I have minus sine of Kx over sine of Ka. And we can see and understand, I think, even the necessity for this minus sign, right? Because when I substitute x equals minus a to match these two solutions together, the sine Kx gives me actually minus sine of Ka, which I would then need this extra minus sign to ensure I get a value of 1, which then matches my exponential here coming to me from region 1. Beautiful. We have one last piece here, and then we can begin to think about what this is really telling us. So let's look at then at phi 3. So here's phi 3, which applies in the region where x then is greater than or equal to a. And I guess, I have been calling this always greater than or equal to on the lower side. It doesn't really matter. We know the wave function's continuous anyway. Very good. So let's look at phi 3. Now, that one will take a little bit more work for us, but not too bad. Now, for phi 3, we have, of course, growing and shrinking exponential pieces. And we already know by design, that's where this condition came from, that the prefactor on the growing exponential piece is simply 0. So I don't have to worry about the growing exponential piece. I just have to figure out what the prefactors are on the decaying exponential piece. And we know how this game is going to be played. Recall that for the hyperbolic cosine function, right? We used this last time. The hyperbolic cosine is the sum of the two exponentials divided by 2, whereas the hyperbolic sine is the difference in the exponentials divided by 2. And so when we substitute in the positive exponentials, that's how we got this condition gives us 0. We are now focused on substituting in the shrinking exponentials, the negative exponentials, and for sine it comes with the minus version. So we simply can now pull out our prefactors. So when we do our substitution, the decaying exponentials in both cases come with a factor of 1/2, and then they have their decaying exponential portion. So let's write that part down first. So we know there's going to be a overall factor of 1/2. There will be a whole set of prefactors, which we're about to copy out, and then there is the decaying exponential piece, which is minus alpha. The particular argument on the hyperbolic functions was written in this way. So let's look at the prefactors now. So from the hyperbolic cosine part, the prefactor, we've already taken care of the 1/2. The prefactor comes in with a positive sign, which then multiplies this entire prefactor. So I get these two pieces in here with a positive sign. So there was a cosine of 2Ka, plus then, I believe it's k over alpha. Is it not? No, it's alpha over k for that term, plus alpha over k times sine of 2Ka. Very good. So that's from the hyperbolic cosine. From the hyperbolic sine, it's the same argument, except notice there's a minus sign that goes with the decaying exponential. So I have minus of these two factors, which will then give me a plus k over a times the sine, and then minus the cosine. So I have plus k over a, or k over alpha, I'm sorry, times the sine of 2Ka, and then minus the cosine of 2Ka. Very good. Here again, we're starting to see some beautiful cancellations. Notice, first, the cosine terms are going to cancel from one another. The sine term is nice. I've got the same sine term on both of these. So let's factor out that sine term. So I've got 1/2, and the sine of twice the angle is twice the cosine of Ka times the sine of Ka. And then that sine of 2ka term, both of those, they were multiplying either alpha over k plus then k over alpha. Now, the first obvious simplification is the cancellation of the factors of 2. The next thing that we have to consider is the value of this sum for our very particular types of solutions. So we have two types of solutions, so let's look at them in turn. So for the type 1 solution, what we know is for type 1, where is he? K over alpha is cotangent. That means alpha over k is the tangent. So alpha over k was the tangent, so that gives me sine of ka over cosine of ka. And then the next term is just the reciprocal of the first term, right? So then that would give me cosine of ka over sine of ka. So that is the value that I would get for this sum in the type 1 case. Now, let's work through, and of course it has these other two functions that come down as well. And we will in a moment look at case 2 in the same way, which will have the cosine times sine. It will have its own particular values for the alpha k terms. But before we go to type 2, let's complete our calculation here for type 1 and see what we get. So this is very nice, actually, because I have a product and I've got ratios. So if I look at the first term, the cosines cancel, and I'm left with sine squared of ka. So if you're looking ahead, you might see exactly what's about to happen. Plus, then, when I look at the second term, the sines cancel, and I have cosine squared ka, and oh, look at this. Look how beautiful it comes out. This comes out just to have a value of 1. Which, in some sense, that, of course, right, is the prefactor that I'm writing down. I had neglected, I see here, to include my decaying exponential, which is fine. So that's 1 times e to the minus alpha x minus a. And the beauty of this is it had to come out to be 1 because look, once again, this function has value 1 when x equals a. And when I attach this function, which is my phi 2, to phi 3 at x equals a, phi 3 at x equals a then better have the value 1. And in fact, it will only if I have the correct prefactor here. Great. So that one makes sense. Again, a very beautiful, simple result. So there's definitely something physical going on here to make all this beautiful math happen. Okay, we finally have type 2 to contend with. So how about alpha over k and k over alpha for type 2? So for type 2, k over alpha is minus tangent of ka. So k over alpha is the tangent. So the tangent is sine ka over cosine ka, because I was substituting in here for k over alpha. But then alpha over k again is just the reciprocal of the term I've written down. So that will give me a minus cosine ka over sine of ka. And we notice that we're going to have exactly the same thing again, except there seems to be an overall minus sign, right? So I will have minus. And actually, if you look at it, once I've picked out the minus sign, I've got cosine over sine plus sine over cosine, which is exactly what I had here, cosine over sine plus sine over cosine. So I don't have to work through all the math yet again. I know I'm guaranteed I'm going to get it sine squared plus cosine squared. If you want to work through the math, they actually come out in the opposite order. But we already know we're predestined to get exactly the same solution as before. So what we end up then is minus 1 times then my decaying exponential, x minus a. And I guess to be completely mathematically correct, I had better make sure to copy these decaying exponential pieces down here. I'll copy it down below. Carry it down through all of the different terms. Great. So let's just write down the solution in its final form. So my phi of x then has then these 3 different regions. For x less than minus a, I had just again the growing exponential piece, x plus a. Right? For x in the in-between regions, what I have then are two possibilities. I either have cosine kx over cosine of ka for the type 1, and for type 2 I have minus sine of kx divided by the sine of ka if I was a type 2 solution. And then finally for the region 3, x greater than or equal to a, I literally have a very simple result. I either have plus or minus, right? So for region 1, I have just e to the minus alpha x minus a. And for region 2, I have minus e to the minus alpha x minus a. Great. So our next task then is to take a look at the let's look at some plots of these functions to see what it is that they're really telling us about the behavior of these wave functions.